All right, well, I'm sort of representing the Liquid Crystal Materials Research Center at CU Boulder, which is now part of the Soft Materials Research Center in our MRSAC. And there's a lot of people have worked on this project over since 2009. And I have a very simple, straightforward hypothesis that very few people believe, but I'll fly it and we'll see what happens. So first of all, this is a bent core story. And of course, we're standing on historical real estate here with regard to bent cores. So, well, not with regard to the original bent core work, which was done in the 20s by Forlander, but the first real disclosure to the wider liquid crystal world of the story of these bent cores giving ferroelectrics from achiral molecules came from Hideo Takazoe, and he was giving a talk right downstairs in this very building. That was the very first time any of us heard about the wild properties of these things. And he actually talked about these PNO, PIMB system. And in Boulder, we sort of did a lot of work with the C9 homolog, and we call it NOBO. Noel made that name up. And so NOBO has this remarkable ferroelectric phases from achiral molecules. At the time, that was really shocking. And but then it turned out that it was even more shocking. So the first disclosure to us anyway was in 96. By 1997, we had the B2, which is a kind of smectic phase that showed the first example of conglomerate formation in a fluid. That is the first example of formation of heterochiral domains coming out of a fluid spontaneously. Spontaneous reflection symmetry breaking in a fluid. That was happening in the B2 phase of NOBO, and that whole story was pretty much understood by 1997. But then Hideo also talked about another phase, B4. We now call that the B4 phase, or the helical nanofilament phase. And it took until 2009 before anybody really understood the B4. And I think we're still actually, it's a very mysterious thing, and we're still working on it. So I'll try to give you an idea. Okay, so here are this beautiful, sort of chiral smectic switching coming from an achiral molecule, and you got right-handed domains and left-handed domains, and that's the first fluid conglomerate. Okay, so, but the B4 is really surprising and incredible. It has, it has this strong rotatory power, and Peter Palfy actually mentioned this in his talk, but I actually believe that this material has the strongest rotatory power of any isotropic fluid. Okay, the strongest, so it's like 0.5 degrees per micron. So in a 10 micron cell, you get a 5-degree rotation, and you can see you got these conglomerates. It's a conglomerate, so you have right-handed and left-handed domains. And if you uncross the analyzer and the polarizer, then you can see the rotated plane polarized light coming out. And remember that in chemistry, if we have a chiral material and we want to measure its rotation, we use a 10-centimeter path length. Okay, this stuff is doing this. You're getting 5 degrees in a 10-micron cell. And I keep trying to hammer on Bart Carr to tell me if this is it really is the strongest rotatory power. Because there are crystals that you can orient the crystal in a specific way, very specific way, and bring the light in and get these kinds of rotations. But this stuff is isotropic. Okay, so I think this is the strongest rotatory power of any isotropic material. It also has some other, the phase space is disappointingly narrow, but that's okay. It's just a challenge for the chemistry. I'm not going to be talking about new bent core materials today. It's all about NOBO. And you get these, the large homochiral domains. And so, I don't have time to go through the details, but Noel worked out the basic structure of the B4 helical nanofilament phase, thinking of it as a kind of smectic liquid crystal phase where you've got these orthogonal rectangular lattices in the top and bottom half layers that cause a spontaneous Gaussian curvature. You end up with this twisted layer structure, and then those layers, and then because of the Gaussian curvature, the layer width and the number of layers is limited, and you end up getting these little nanofilaments that spontaneously limit to about 30 nanometers on a side, And yeah, what this makes, so because of this negative curvature, you end up with a square cross section. So it's the number of layers, and then the width of the layers determined by the strain that comes from trying to make them wider because of the curvature, and this tendency of the top and bottom half layers to stretch in orthogonal directions. And then there's the layer number ends up giving you about the same height as you have width. And so this thing has a square cross section. It's this twisted, curvy thing. And actually, you see these things all over the place. You know, this is what we think they look like, right? So you just, you know, it's got a square cross section. Now, the layers are vertical in these pictures. You know, the bricks are not the layers, okay? The layers are vertical. It's really a smooth, it's just a square. Just take a square in a, you know, well, start with a, you know, close packed array of circles in a hexagonal array, okay? And then put these helical nanofilaments in there. Start with a square at the bottom of the circle, and then just sort of rotate the square as you go up smoothly, okay? So, you know, you don't have, these blocks aren't there. It's just a smooth rotation. And here is this beautiful sculpture in, you see the car down here. These things are huge. That's in Barcelona. Here's this giant building in Dubai that has the same basic structure, except that this one it doesn't have a square cross section. It's kind of interesting, but anyway, so that's kind of what we think these things look like. All right, and here's the transmission electron, the freeze fracture TEM, showing what they look like. This is glass. Here's the filaments on the surface, and here's a close-up of the filaments, and here these are plastic models of these things. And you know, so we think that, you know, this is looking kind of like this, and that's what you're seeing in the TEM. And yeah, and here's this beautiful homeotropic, you know, AFM image of a homeotropically aligned B4 that Daniel Kroeke got back in about '97. And so these are the ends of the layers. So you're looking at these things from the top. So you're looking down on top of these squares that are inside these circles, inscribed in these circles. Okay, so you know, you notice all the layers are parallel. That must mean that there's a plane where all the edges of these squares are parallel. If you go down or up, you know, going vertically, if you go down or up, then that's no longer true. It looks like that. And so actually, this is a very porous structure. There's these holes that you can't avoid, and it's about 45% of the area is free, or the volume. About 45% free volume if the helical nanofilaments are oriented like this. Okay. Okay. Yeah. With the neat material, you can actually nicely fill space by doing a few little slight rotations or offsets. I'll show you that. But it is actually, you can get rid of that 45% of free volume. Not here. There's no way to get rid of it here because of the, you know, the tops of the squares, you're seeing them. There's this plane that has the tops of the squares parallel like that. If you go down, you can't avoid having these holes. Okay? But if you allow the things to change in some way, you can fill the space. Yeah, you get these. Yeah, it's easy. You know, I mean, looking at models, it's equally easy to make homochiral pairs or heterochiral pairs, and you know, we have to explain why you get these huge homochiral domains when this sample grows out of the isotropic. And Randy and Sabeta Matsumoto showed that you can get these things, you know, in a fluid phase. This could be a kind of fluid smectic. And that's certainly what Noel was thinking, what most people were thinking. Well, everybody. But, okay, there's only...
Noel sent us an email and asked us if we could figure that out.
He did?
Yeah, so it wasn't...
I didn't know that.
It wasn't random.
Well, you did it. So, you know, so it could be a fluid smectic. But the hypothesis that I'm going to try to sell you on today is that it is not a fluid smectic. It's actually a kind of nanocrystal. But it's a weird nanocrystal, so you know, we'll get to that. But yeah, these things, I think, are much more like crystals than they are like fluids, even though it would be possible for them to be fluid. Okay, so this is what I'm saying here. In my humble opinion, these things are a kind of nanocrystal, and that comes from analysis of a ton of dynamic C13 solid state NMR data. So here they are. So This is the orientation where the squares are parallel at the top and you have all these holes. But if you just let it slip a quarter of a pitch down, then you can fill the space. If you rotate the two filaments a little bit, you can fill the space. And you can fill the space with a heterochiral pair perfectly well. You take a right-handed and left-handed filament like this and stick them together, you can easily close pack them. Okay? So then there's this mystery of why you get these large domains. Okay, homochiral domains. Why do these things want to come out of the isotropic and make very large right-handed domains that are pure right-handed and very large left-handed domains that are pure left-handed? And I think what it is that a kind of crystal, one of the characteristics of crystals is that they are slow to nucleate but very fast to grow. This is often true, and you often get spherulites when that happens. And these are they come out as a kind of spherulite. Not necessarily, but out of solution they come out as a kind of spherulite, I think. But really the reason you get those huge homochiral domains is, believe it or not, all the nanofilaments in one of those domains, they all came from an original single nucleus. And that nucleus, you have nuclei, subcritical nuclei that grow and shrink and grow and shrink, and then a nucleus gets critical and whammo, the thing grows really fast. This is very typical in crystals in the solid state. Okay? And so I think that's what's happening with the helical nanofilament. So you see that big right-handed domain. Well, that all came from an original right-handed nucleus, and then somewhere else a left-handed nucleus nucleated and started growing. And the rate of growth versus the rate of nucleation determines the size of the domains. Okay, so yeah. But if you take a single layer of an H and F and kind of squish it out and flatten it and do electron diffraction, it looks a lot like a smectic E, or kind of tilted smectic E, where you've got where you've got this rectangular lattice. So the model was that it was a kind of liquid crystal, kind of smectic E-like in the layers, and so I kind of didn't buy that because of the reflection symmetry breaking. Of course, we know now that that's possible, but yeah. So the whole reason for doing these experiments was based on a wrong assumption, which is you don't get reflection symmetry breaking in achiral liquid crystals. Actually, you do. But I think in the B4 case, it's much more like a crystal. So with the solid state NMR, you can, well, okay. It turns physicists invented NMR, but they haven't really kept up with it very much. And it's become the tool of chemistry, right? As opposed to a microscope, we use NMR to determine structure. And you can use solid state NMR. And so what you see is you can measure very slow conformational dynamics by solid state NMR. So if you, like for example, this is a crystal, this 28 OBC, beautiful mesogen, and has lots of really nice phases, including there's 3 crystal modifications and a smectic E, smectic B hexatic, smectic A. Okay? And if you look at this stuff in the crystal phase at room temperature, you see that these 2 carbons, okay, I mean, this gets to the diastereomers versus enantiomers thing, and the homomers. Homomers, of course, are congruent. Okay? But it's even more complicated because it's dynamic, right? So the barrier for spinning around this bond in the liquid phase is very low. It's called a pi flip. Okay? So this starred carbon, C1, and this carbon, C2, exchange locations. Okay, site exchange, they call it. That happens so fast that we don't even think, we don't think of them, we think of these 2 carbons as being homotopic and not enantiotopic. They're the same. Those carbons, if you have rapid exchange, then, we ignore that. You can get conformations by rotating around this bond that are chiral. This molecule is not chiral. It can't be resolved, even though it has chiral conformations. This is all this dynamic conformational dynamics. And I really think that the definition of a liquid crystal has more to do with conformational dynamics than anything else. Okay? So, so you can tell at room temperature that these 2 carbons are giving 2 peaks in this solid state carbon NMR spectrum. The fact that they're giving 2 peaks means that they can't be the same. They can't be homotopic. They can't be existing in identical environments. And if you freeze that rotation, you can see that one of these carbons is next to that carbon, and the other carbon is farther away from that carbon. They're different. They're called, they're heterotopic, so, or diastereotopic. So they have to have, well, they should have by symmetry different chemical shifts in the NMR. But okay, here's the cool thing about NMR that you might not have thought of, and that is that these things are separated by 760 hertz, but the actual frequencies are in the megahertz. So it's like parts per million difference in these frequencies of these absorptions. Parts per million. Okay? So in order to be able to see that, you have to look at it for a long time. It's the Heisenberg uncertainty principle. Okay? So if those carbons start exchanging sites, once that gets fast enough, and it doesn't have to go that fast, then those two peaks, as you heat this up, the rotation around this thing starts to happen. Okay, it might be happening really slowly in the crystal at room temperature, but as you heat it up, it starts going faster, and you get to a point where you just see what's called coalescence. That's a quantum mechanical effect. You can no longer resolve the peaks because they're exchanging too fast, and those frequencies are too close together. Okay, and then as you keep heating it up, then it just turns into a sharp singlet, which is what you would see in solution, because that rotation is happening really fast. Okay, so from the location, the temperature where the coalescence happens and the frequency difference, you can easily calculate quantitatively, the barrier for doing that pi flip in a crystal. And a lot of people have come up to me and say, well, if the ring can flip, then it can't be a crystal. That is not true. There's lots of dynamics happening in crystals. They're just really slow. Okay, so what's happening is the barrier is 13.7 kcals per mole in this case, which is a pretty high barrier, and the exchange is slow. And I'm not sure exactly what the rate is, but it's pretty slow. But you can easily measure that. This is a kind of real-time quantum mechanics going on here. And when you see this coalescence, it tells you how fast this exchange is happening, the site exchange, how fast these two things are exchanging locations. And in the crystal, they sort of flip. It's called a pi flip because they flip between two states that are indistinguishable, two conformations that are indistinguishable. But the NMR can tell the difference, at low exchange rate, and then it stops being able to tell the difference when the rate gets fast enough. Okay, so it looks kind of so. All right, this stuff actually has a semantic E, but you can see that this is the top of the crystal 1 phase. So it's still a crystal up here, and you're seeing a singlet. So that means that pi flip is happening fast enough to, be unable to observe the splitting. You can't resolve those two peaks because, it's flipping too fast. That's in a crystal. So then you can keep heating up into a second crystal phase, and then you can go into a semantic E. So we were really interested to know what the barrier. Okay, so in NOBO, the bent core that makes the helical nanofilaments, that pi flip barrier is 17 kcals per mole, which means that it happens at room temperature once every 2 seconds. That's the kind of dynamics that you can probe by solid-state NMR. That flip is happening once every 2 seconds. And for a chemist, molecules live in this world that everything's really tiny and everything happens really fast. I mean, once every 2 seconds is like infinitely slow in molecule world. Okay? And it happens in a crystal, a full-on solid crystal. That happens. It happens in crystals of amino acids with benzene rings, and it happens in any crystal that has aromatic rings. Okay? So in the solid-state NMR, this helical nanofilament phase, the molecules are thinking that they're in a solid. Okay? That's what this says. The semantic E, of course, you can't say anything about the semantic E here because it's already, you already have a singlet. You heat up into the semantic E, it's going to stay a singlet because the flipping is already happening too fast. But we looked at a really low temperature semantic E. Well, it doesn't have to be low temperature. We looked at a semantic E that, well, it was at 2 degrees. It transitioned into a crystal, and I guess I don't have the details of that. But looking at another semantic E that we could cool it down more in the semantic E phase. You see broadening. You never see two peaks, but you see broadening. And by analyzing the peak shape, you can calculate a 7 kcal per mole barrier for a semantic E. 7 kcals, that's, and the rate is kind of exponential with the barrier height. So 7 kcals is much faster. 7 kcals is like a fluid. Hydrogen bonds are like 5 kcals, right? So 7 kilocalories barrier is a very small barrier. That's like a fluid. So a semantic E is a true crystal. It's got long-range positional order in 3 dimensions. And yet the molecules look like they're in a fluid. People would call it a rotator phase or whatever you want to call it. The B4 does not have long-range positional order in 3 dimensions. It does not. So it's not a crystal. Those helical nanofilaments are not crystals. And yet within an individual layer, I think the individual layers are crystallized. It's just there's no correlation across layers. And that, within an individual layer, the molecules think they're in a crystal. So it's so you have this strange situation where the symmetric E is a crystal, but it's very fluid in terms of conformational dynamics. The B4 is not a crystal, but it's very crystal-like in terms of conformational dynamics. And I think this conformational dynamic, this speaks to a lot of things that are happening in liquid crystal world, conformational chirality and things like that.
Okay, sorry, do you mean in a layer or in one of those square?
No, in one layer of the square thing.
Each layer is independent?
Each layer, there's no correlation across the layers within a single helical nanofilament. So you've got a layer of crystal, then you've got these 2 layers of hydrocarbon, and then you've got layers of crystal, right? And those, those things apparently, they're not correlated. They could slide across each other. At over 110 degrees, this thing actually does flow. It is a kind of liquid crystal. It's a liquid crystal of these crystalline helical nanofilament. Okay, so yeah, so this is this is sort of a close-up of this thing, and let's see, when do we end?
Yeah, we still have 7 minutes.
Several minutes? Okay, well, I got about an hour to go.
Yes.
No, I'm supposed to end at 1:10?
No, and the officials after talk should be the 2:05.
Oh, okay, sorry, 2:05, okay. So I got 10 minutes, almost 10 minutes. Okay, so good, that's fine. So, here's this this TEM image of these helical nanofilaments. Here's the edges, here's edges of layers. Here's C9 hydrocarbons sticking out like a self-assembled monolayer. And so half the surface area of this thing is edges of layers. Okay, so I'm telling you we have a liquid crystal phase of nanocrystals that are about 30 nanometers in diameter, 5 to 8 layers of these crystallized things, okay, these bent core molecules. Okay, so they're about 30 nanometers. The size of the squares are about 30 nanometers. And it's got this twist, and so that means that half the surface area is layer edges and half the surface area is faces of layers or C9 hydrocarbon. And this phase, the most amazing thing about it, it's a liquid crystal of these nanocrystals. It's a hexatic liquid crystal of nanocrystals, and this phase can accommodate almost anything, up to like 50% by volume. Almost anything. I mean, it's amazing how you just, melt the NOBO and stick something in there 50% by volume and cool it down, and the guest, it's a host-guest thing. Really, we're doing host-guest chemistry in the helical nanofilament phase. So you cool down, and the guest is nano-confined. So this is 50% by weight, or about 50% by volume, 5 CB. Or maybe it's 8 CB in the helical nanofilament phase. So you start cooling, you have a 50-50 mixture of these two things. You heat it up until it's isotropic. Then you start cooling, and the helical nanofilaments come out of the 8 CB, which is just acting as a solvent. Okay, you get slow nucleation, very rapid growth, and you get these large heterochiral domains. And the 8 CB, you can look at, cool all the way down to room temperature, and the ACB has a symmetric, and you can see from the peak width at half max of this peak from Brookhaven, the X-ray scattering from Brookhaven, that this thing is nano-confined. It looks like ACB in an aerogel. And the helical nanofilament, if you go to higher concentrations, it starts to bulk phase separate. Okay, so the helical nanofilament phase can somehow accommodate about 50% by volume of almost any guest. Okay, which, yeah, and so here's, you still get the conglomerate. Okay, so, this is this mixture of 50% ACB and NOBO, and you can see right-handed and left-handed domains. So this is, you uncross the polarizer and analyzer, and then you rotate the polarizer the other way, and this gets bright, starts out dark, gets bright. So you got this is, the ACB is in there. Okay. If you go to higher concentration of 8CB, you can see this beautiful spherulites growing in here, but the 8CB bulk phase separates. And here you see, bulk phase separated 8CB. This shows a really broad peak. And here's a sort of a spherulite that has 8CB in it, because the B4 itself has almost no birefringence. So there's 8CB in here. Where is it? I'm not sure. I don't know where it is. But it's in there somehow, and it's nano-confined. Okay, and here you're off the electrode. You put a field on, you can switch the bulk HCB into homeotropic. It just turns black, but the stuff that's in here is kind of still showing birefringence. And Noel and Joe McLennan and Matt Glazer have done a beautiful job of understanding how these liquid crystals will orient inside these domains. Okay, what we think is, this is just the argument restated, right? You can see here exactly how you make the spherulite, right? You had a nucleus, it started growing. These filaments are budding off the original nucleus and filling a sphere, and they're all the same handedness, the ones that came from that original nucleus. And yeah, so what happens if you put a chiral nematic in there? Okay, this is chirality at the nanoscale. If you put a chiral nematic in, something really interesting happens. So you get the spherulites, and this is a right-handed and this is a left-handed domain. Well, these are all right-handed helical nanofilament, right? The helical nanofilament, this is a domain that's oh, sorry. These are right-handed and left-handed helical nanofilament, but the liquid crystal is all right-handed. Sorry, yeah. So, we're putting in chiral R, 70.5 star. Okay, that's chiral, single enantiomer, right-handed. Okay, you got right-handed and left-handed helical nanofilaments. So that means that this domain that has the left-handed helical nanofilaments host for the right-handed guest is diastereomeric with respect to this right-handed helical nanofilament domain that has the right-handed guest. So this is right-right and this is left-right. Those are diastereomeric. That means they are different. They're not mirror images. They're just different. Okay? That means they have different physical properties. And if you start heating the sample, they behave differently. So let me try to heat the sample. There we go. One of them extinguishes. Then they both come back out of extinction, and then they extinguish totally. Okay? So that's this diastereomeric behavior that you expect when you have left-handed, right-handed, and right-handed, right-handed. Those things behave differently. And what it is the nematic, aligns on the surface of the helical nanofilaments in a very specific way. The nematic twist is always the same, but you can have right-handed or left-handed helical nanofilaments, which are sort of mirror image related. And Noel and Matt and Joe figured out exactly what's going on here, and it would take about a half hour to tell about it. But this is, and so somebody asked a question at a meeting, why is that happening? And Noel said, it's the diastereomericity, which is so cool, I just love that. Because it's kind of liquid crystal, or sort of mesogenicity mixed with diastereomeric, But unfortunately, the referees wouldn't let it in, which is really too bad because I think it's a cool word. But anyway, there's chirality at the nanoscale. And so half the surface area of these helical nanofilaments is edges of layers. And we've got this organic semiconductor where we have this semiconductor aromatic crystal, and then we have these tails that are insulator, and the crystals are making direct contact with the ambient at the ends of the layers and at the edges of all the layers, direct contact with the ambient. And we have this way of making, and these things all make composites with helical nanofilaments. All these things, and also solubilized fullerene. C60 won't go in. That's one of the few things that won't go in. But PCBM, which is a solubilized C60, will go in and make a 50% by volume composite with nano structured composite. Actually, there's this Cullen Knuckles has this aromatic helical ribbons thing that melt at above 300 degrees. So you put that in, it's soluble in the isotropic of NOVA, but you cool it down, and when you go into the B2 phase, Cullen's stuff crystallizes out. So we weren't able to get those ribbons into the helical nanofilaments, but that's something we're going to do that. I'm sure it would work if we had an isotropic to B4 material. So this is a perfect setup for making a bulk heterojunction, right? For making a solar cell. You have these blobby domains in a typical bulk heterojunction solar cell. One of these domains absorbs the light. You get excitons. They migrate to the interface. The exciton splits. You end up with holes and electrons that go to the electrodes and collect your electricity. Okay, so it would be a lot better if you could sort of have some control of the morphology of this heterojunction. Everybody understands this. Okay.
2 minutes.
2 minutes. Okay, so yeah, so and you can get them aligned. Don Ki-yoon is really good at aligning these things in various ways. He can actually get this homeotropic alignment, which is really almost perfect for a solar cell. So here you're looking at the tops of the helical nanofilaments, just rotated that on its side. This thing is nanostructured like this. You got the electrodes like this and this. There's this. This is a bulk heterojunction, perfectly oriented for a solar cell. And you spin cast these things onto quartz substrates, and you get these beautiful spherulites, squished down spherulites. You do Gary Rumbles' time-resolved microwave conductivity experiment, TRMC. He's at the National Renewable Energy Lab in Golden, and it's close to us. And we shared a grad student. And what you see is that you get, you flash the PCBM, the C60 stuff. Well, this is actually C60, a thin layer of C60 on top of the helical nanofilament phase that's doped with, that's neat. And, and you generate excitons in the C60. They come to this interface. They split with near unity efficiency. Every absorbed photon creates mobile charge. There's a lot of arithmetic that goes into this and a lot of interpretation of a huge amount of data, but that's kind of where we are. And then the recombination is slow because the signal lasts a long time. For those guys, 400 nanoseconds is a long time. Okay? So then we tried a bulk solar, a bulk heterojunction like this. The C6, this is PCBM, solubilized fullerene. It's going in like this. Kind of, I think it's kind of touching the layers. But I don't know. I don't know really where it is. It's in there somewhere. You can't see it. Okay? And if you have the helical nanofilament phase, you get a pretty darn good signal in the time-resolved microwave conductivity experiment for this stuff, meaning it's good at splitting excitons. Okay? If you anneal it, the idea was we would anneal it, improve the morphology, cool back down, and get something that was better. And what happens instead is the signal totally disappears. No signal. And so what's up with that? And when you do the, the TEM on the substrate, and what you find is you have helical nanofilaments before the annealing. When you anneal, the surface kind of makes the layers go flat. You melt it and cool it back down. You're in a very, very thin film. The layers go flat, and that expels the PCBM. And so the PCBMs are sort of floating in these little, sort of 50 PCBMs diameter balls on the surface of a flat smectic. There is no way you can irradiate one of these things and split the exciton through, C9 hydrocarbon. That's not going to happen, and it doesn't. So the morphology beautifully matches what you see in the experiment, which is really rare and in this business. And so we're excited by that, and we're going to keep working on it. And there's Noel, and hi Noel. This has been, so we're sorry you're not here. These are the several other people that have been working on this project for many years. There's Rich Shoemaker, our solid-state NMR expert. I thank them. I thank you for the invitation.
Okay, question. Yeah.
So, Dave, you described the cross-section of the nanofilament as a square.
I do.
Right? And so why is it a square instead of a rectangle?
Well,
right? Because there's no symmetry.
It's because you can't fill space with negative curvature, and so the farther away you get from the center of the ribbon, the farther the curvature is from the ideal that it wants to be, and you get to a point where there's just too much strain. If you made it wide enough, there would be no curvature on the ends. And so that's why they self-limit at about 30 nanometers width, and then you have a finite number of layers, and they end up being about the same width.
So that self-limiting mechanism works in both dimensions.
Apparently it does, yeah.
So it gives the same length.
So you end up with something that has a square cross-section, and that Noel seems to be totally on board with that. It fits with all the TEM data. And also you saw Kroika's homeotropic. Of course, it's hard to tell how wide the filament, how many layers there are in each individual filament in that image. But that's what we think. It's a square cross-section. So that's why, and it doesn't keep growing. I mean, and what happens when you just cool out of the isotropic or cool out of a smectic? Is it making these things that are porous, but then there has to be something filling it? But whatever it is that's filling the pores in the neat stuff, if there are any, it can't be fluid. Otherwise, we'd see it in the NMR. It would stick out like a sore thumb. It's 45% by volume. Right? There is no fluidy stuff in there. It's just all locked in. So I tend to think that it's one of those slip things that fill space. And it just makes this, it makes these things just fit together, and that's what the neat helical nanofilament phase looks like. And that's what has this gigantic rotatory power. It's a supramolecular assembly with lots and lots of molecules, and it's really chiral, and I think that's why it's got such a, world record-breaking rotatory power in the visible, or, yellow or whatever it is. Okay. Yeah.
In respect to the rotatory power, we used to think about G factor. It's the ratio between the difference in epsilon left and epsilon right over
What's
epsilon.
circular birefringence?
Yeah. Is there any conversion from the rotatory power of 0.5 degrees by microns to the G factor, maybe?
Well, the Z factor. I mean, the Z factor allows you to calculate the rotatory, the circular birefringence. Then there would have to be, because this thing has huge circular birefringence and almost no linear birefringence. The reason you can see the circular birefringence is because the birefringence of the B4 phase, the linear birefringence is almost zero. Between cross-polarizing analyzers, it's very, very dark. So you have so there's no background linear birefringence. So you can see this circular birefringence, which is huge.
Yeah.
And Knoll and Lauren Huff, sort of did a calculation of that, but they were assuming a fluid. To be honest, very few people actually buy this argument about the crystallinity because they don't get the solid state NMR, data. But I don't know. I mean, I'm not in a position to be able to tell for sure myself, but Rich Shoemaker is a world-class expert at this. This is what he says, and he goes through the analysis. It sounds good to me. So, but this is the kind of thing you have to spend your career at.
I actually absolutely do not have any concerns
No problem?
about
See, because you
crystallinity.
understand it.
Yes. I'm just trying to convert it into the structure and the dependence between absorption and rotation.
There's almost no absorption.
Yes, I mean, that's interesting.
Yeah.
It's all
There's almost no absorption, and there's almost no linear birefringence.
And that kind of interesting to me, because if there is a lot of rotational activity, that means that there should be some oscillatory shift
Well,
of the
it's an organic
electrodensity.
semiconductor. I mean, it could, I don't know if there's actually electrons jumping from molecule to molecule inside a single. There's about 80 molecules. These things are about 80 molecules wide, the filaments. And then there's 8 layers or 6 layers of those 80, stacked on top of each other. Why that gives us such enormous rotatory power, I'm not sure. But, just getting somebody to believe that it's actually, interesting and unique, I find it totally unique. There's nothing else that does this. Isotropic material that has that kind of rotation that I know of.
Okay, Peter is the last question. Peter.
Mechanical properties, do we know anything about viscoelastic properties?
No, I don't. I don't know that anybody's studied that. I mean, you can align these things. You can align them by shear. I can tell you that. If you have neat NOBO and you heat it up above 110, below 110 it freezes into a glass. And you can't shear the plates. But if you heat it up, we think the tail, in the NMR you can see a signature of the tails melting. We think the tails are melted above 110, but the cores are crystallized. Because the diastereotopicity of those carbons never goes away all the way up to the B2 phase transition. So you've got this crystalline rigidity all the way up to 155. But between 110 and 155, it's fluid. It's a hexatic liquid crystal of these big rods. I mean, if you think you could get, by studying the viscoelastic properties, you could get, some information about what these things really are, that would be great. And by the way, NOBO is pretty cheap, I would say. I mean, you have to make it, but it's not that hard. It's a shift base. Maybe the undergrads could make it.
Not stable then.
Pardon?
Not very stable.
These things are very thermally stable, but they're not stable to water, especially water with a little acid in it. So yeah, if you heat it up to 150 and you're playing around on the microscope for a couple of days, the phase starts to change. But it lasts for a while. even under those conditions, just open, you know. So they're not, I mean, I used to think shift bases, forget it, they're useless practically because they're too unstable. But if you keep them away from air and water, they're a rock. They're more stable than esters.
Okay, it's very, very beautiful the talk. Okay, I guess have many questions because yeah, thank you very much.